Hello, everybody.
Hello.
Hello. Just as a reminder, we are recording this as every time so that you can get to YouTube and review these at your leisure. Is everybody getting the notifications on Blackboard for the little code thing that gets you to the YouTube videos? Are you guys able to access those?
Yeah.
Yeah.
Okay, great. Alrighty. So does anybody have any questions that they would like to ask at the beginning here? Any questions about the homework? Let's see, homework 2 is due tonight, right? Anybody have any questions they'd like to ask? Okay, and remember, you can interrupt me at any time if you have a question you'd like to ask. Again, we're trying to make this as this virtual environment as much like being in the classroom as we can. Where in the classroom, of course, you would stop me at any time and say, oh, I don't understand. What are you doing there? So please do that here. If you don't like trying to find a pause and interrupting me, you can always ask a question on Zoom group chat and I will catch those. And if it's a question that you feel is embarrassing just to even ask the question, then send me a private chat. Okay, just a reminder, please ask questions as we go through this. Okay, so today's lecture, lecture number 4, is we're going to start with talking about stresses again. We're going to pick up where we left off with talking about stress. And I wanted to work through a truss example, just in case it's been a while since you've done a truss in statics. I thought it'd be a good refresher for everybody. So we're going to work through a truss example 1. And here's our truss. Pretty simple, but I made it non-symmetrical. So you can see the slope on these 2 members is twice the slope of these 2 members. And I did that on purpose, so you can see how this works out. All of the necessary dimensions are here for you, except for maybe B is located halfway. So that's 20 feet to B, 20 feet to C, 10 feet to D, 10 feet to E. So that part of it is symmetrical. So given, for this particular problem, all the members have an area of 4 inches squared. Just keep it simple. And the rest of it is just in the geometry. Here we have our end reactions at A and E, and the applied loads are 20 kips at B, 40 kips at D. So what is required, I just picked out 2 of these. I want to find the normal stress in strut AB and in strut CE. We could, of course, solve them all, but once you get the hang of solving a few, I felt that would be enough to illustrate the problem. So any questions about the setup before we go into it? Okay. Like most problems, the first step of most problems is to find your end reactions and to draw a free body diagram in order to find your end reactions. So what we're going to do is we're going to sum our moments about A. Let me back up here for a second. So we're going to sum our moments about A. I didn't draw a free body diagram of the whole thing because it's pretty close to what you're looking at right here. But we're going to sum our moments about A. So you have 20 times a moment arm of 20 feet. You have 40 times a moment arm of 40 plus 10 is 50 feet. And your unknown reaction at E at 60 feet. Okay, so here's your 20 times 20, 40 times 50, minus unknown reaction R, E in the Y direction times 60 feet. REY is 40 kips up. If I sum my forces in the y direction, I have up my reaction at AY, minus 20, minus 40, plus the 40 that I found for E equals 0. RAY is 20 kips up. Sum the forces in the x direction. RAX is equal to 0. So there are no forces in the x direction, but please remember that if we're looking for all of our reactions, there is an unknown reaction in the x direction that does need to be reported as 0 if it is in fact 0. Okay, so now I have all of my reactions. Now what we're going to do is use the method of joints to solve this truss. Just a quick survey. You have all done the method of joints in your statics. Yeah, not statistics. In your statics class, you've all had method of joints to solve a truss?
Yeah.
Yes.
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 Okay, hearing a lot of yeses. It may have been last year, it may have been many years, but you've seen this before. That this is a review, not like introduction to new material. Okay. So using the method of joints to solve this truss, starting with joint A, and why would I start with joint A, by the way? I start at joint A because there's only 2 unknowns, and at joint A, there's only 1 unknown in the y direction. So that's a good place to start. If you're wondering where you should start, try to find a place that is isolated and you can directly solve for your first unknown. So starting with joint A, we draw a free body diagram of joint A with our known reactions, loads applied, and unknown forces drawn as tensile forces. Okay, so here's my free body diagram of A, just joint A. Again, we solve for our reaction at A is 20 kips up, so there's my 20 kips up. I do not know the force in AC. I do not know the force in AB. So I draw them as unknown and I draw them as tensile forces. But I do know the angle of this strut is a 3, 4, 5 triangle from the original geometry. So I put that on there to indicate the angle of the truss. Now, because in a truss, everything is pinned, all joints are pinned, so there are no moments developed anywhere inside this truss. None of these struts have any bending moments. So that takes away one of our degrees of freedom. So what that means is I only have 2 equations for my degrees of freedom. I can sum forces in the y direction. I can sum forces in the x direction. Summing moments doesn't get me anything. Okay? So I start summing the forces in the y direction because as you can see, I have 2 unknown components in the x direction. I only have 1 unknown in the y direction. So I'd rather do the simpler one first. So I sum my forces. I have 20 kips up. I have 3/5 of FAB up, and that's all I got. So that equals 0. So FAB is minus 33.33 kips in compression. It's negative, so that means my assumption that it was pulling away is incorrect. It's actually pushing down, and that tells me it's in compression. Summing forces in the x direction now, I have minus 4/5 of FAB that I just solved to be 33.3 kips. And that is pushing, so it's actually going to the left, so I put it as negative. My sign convention is up is positive, down is negative, to the right is positive, to the left is negative. Okay, so this is not necessarily negative because it's compression. It is negative because I now know that the force is pushing, or that component of the force is pushing to the left. So minus 4/5 times 33 plus my FAC is pulling to the right, so that's positive. And that solves to be FAC is 26.66 kips, and it's positive, so it is the correct assumption that it is in tension. Okay, so that's joint A. Any questions on what I'm doing? Did you guys hear that?
Yeah.
Yep.
Okay, well, that's a 55-pound black lab who decided that something that she heard outside was definitely worthy of barking at. Sorry about that. I don't know why she's even in here, but okay. Joint B. Okay, we see her. I don't know. We'll see if we have any time left at the end, or if she's still in here by the time I get through the end of this lecture. We'll see. Where was I? Joint B. So you draw your free body diagram and you progress along this, because before I solved FAB, this was an unknown. And so I had 3 unknowns at one joint. I can't solve that joint. But if I solved FAB, now there's only 2 unknowns. And so you can progress along the truss from joint to joint in a logical order, always maintaining not more than 2 unknowns at any joint. So that's what I've done. So I still have 2 unknowns. One of my unknowns is in the Y. 2 of my unknowns have a component in the X. So I start with my Y forces, sum the forces in the Y. I have minus 20 applied at the joint. I have a positive, sorry, let me back up a moment. Sorry. We solved that this 33.33 kip force is in compression, right? And you remember that I told you that this is minus 33.33 kips. The minus was only there to serve to tell me that it's in compression. Once I know it's in compression, from then on out, I'm going to draw it in compression. I'm going to draw it the way that I know that it is. So that's why this one is drawn in compression. These are unknowns, so they're drawn in tension. Okay, does that make sense?
Yes.
Okay, so this is in compression. So it's pushing up. So it's positive because, not because it's in compression, it's positive because it's pushing up, the vertical component of this. And the vertical component is 3/5 times the 33.33. The slope on BC is the same slope, so that's 3/5 as well. And it's pulling down in tension, so I put that at minus 3/5 FBC. I solve this, and guess what? FBC is equal to 0. There is no force in FBC. Sum the forces in the x direction. I have 4/5 of 33.33, plus I have 4/5 of 0, plus I have FBD. And so I can solve that directly. FBD is minus 26.66 kips. That, again, just serves to tell me that it is in compression. And so now I know it's actually compressing, not pulling. Now we move to joint C. And joint C was directly below joint B, or I'm sorry, not directly below, it's off to the side here. So we know that BC is equal to 0. We know that AC is equal to 26.66 in tension. And then we have our 2 unknowns, CD and CE. This triangle was a 2-3 radical 13, not quite as classy as a 3-4-5 triangle, but still. Or you could always just figure out that the theta is equal so many degrees, and then instead of using a 4/5 or 3/5 triangle, you could just use sine of theta, cosine of theta. Works just as good. So again, kind of repeating the pattern, I sum the forces in the y direction. I have 0. I have 3 over radical 13 times FCD equal to 0. There's nothing else in the vertical direction. So FCD is also equal to 0. Sum the forces in the x. I have pulling to the left, 26.66, so that's minus. I have 2 radical 13 times 0, and I have my force in this FCE pulling to the right. So FCE is 26.66 kips in tension. Moving to joint D.
Oh, wait, can you go back real quick? I'm sorry.
Sure, sure. Yes.
So why you want to solve like for joint D while you can like solve it for the stress directly? Because now you have FAB and FCE.
I'm just being complete. Yes, no, you're absolutely right. Remembering that the problem statement was just looking for A, B, and C, E. This is as far as you would need to go because now you have the forces to find the stresses. No, you're totally right. I just wanted to go through an example of the whole truss so you get the whole picture. That's all.
Thank you.
Okay. So joint D, we have our compressive force of BD. We have 40 kips applied. We have our 0 force from CD, and we have an unknown FDE force drawn in tension. So I sum the forces in the y direction, and I have minus 40. I have 3 radical 13 times 0. I have minus 3 radical 13 times unknown FDE. So typo. I was wondering how long I get to the first one. Pardon me for a second. I'm just going to write these down. FBC becomes FDE. Okay. But the value is correct that FDE is minus 48.07 kips in compression. And sum the forces in the x direction. I have to the right 26.66. I have to the right 2 radical 13 of nothing. And I have to the left, because this is now compression, 2 radical 13, 4807 equals 0. And so what does that mean? Well, there's no unknowns in this summation. So this is one of your checks. If this did not equal 0, this is how you know, oh boy, I made a mistake someplace because this had better equal to 0. Then we go to joint E, our last joint. And as you can see, there are no unknowns now on joint E. Everything's been solved for, but there's still utility here. I can still sum the forces in the y, and I have minus 3 over radical 13, it's minus because it's pushing down, times 4807, plus my end reaction of 40 pushing up equals 0. Again, this is a check. If I don't have that, if this doesn't equal 0, I made a mistake somewhere. And lastly, I can sum the forces in the x. I have pulling to the left, minus 26.66. I have pushing to the right, 2 radical 13, 4807, and this had better equal 0. So by the time you're done, you should have 3 checks to be sure that everything added up correctly. Why do I have, is that random? Why do I have 3 checks? And I believe the answer is,
would it be because there are 3 equations of static equilibrium?
yes. I believe that is correct. The whole truss that we started with in the very beginning, that whole truss is a rigid body. And that rigid body has 3 degrees of freedom. So as we go through and we're solving all the joints piece by piece by piece, you're going to end up with 3 checks because we had 3 degrees of freedom.
So it doesn't matter which equation you use because you use 2 forces and x equations instead of the moment equations?
I think you have a good question. I'm just not fully understanding. Could you say again?
You said there's 3 checks, so would you use the 3 equations, the forces in y, x, and the moments to find those checks? Because yeah, you use the force
No.
and X, Y. So it doesn't matter?
Well, again, because the truss has pins at every one of these joints is a pin, because of that, you can't sum moments when you are looking at joint to joint to joint.
Mm.
If you use the method of sections, then you can, well, depending on how things shake out, you might have summing the moments might work with the method of sections, but not with the method of joints. So you're not specifically using sum the moments, sum the forces in the Y, sum the forces in the X, but you don't always have to do that anyway. You have 3 degrees of freedom. Sometimes the way you find the answer is you sum the moments about, say, A, and you can sum the moments about, say, D, and then sum the forces in one direction. It's not always moments X and Y. It's just 3 independent methods to get to all of your unknowns. Okay? So when you're going through joint by joint by joint, again, it's not specifically sum the moments, sum the X, sum the Y. It's just that by the time you're all done, you should have 3 checks on that because you had 3 degrees of freedom.
Okay.
Okay,
Thank you.
no problem. Okay, so now that each member force has been found, remember that the normal stress is equal to a force over an area. So the force in AB was a minus 33.33 kips. It was in compression, divided by the 4 inches squared of all the pieces had the same area. So the load in AB is minus 8.33 KSI in compression. Bear with me a second, I got this distraction. Blah, 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 blah. Okay. So 8.33 KSI, and it's in compression. For CE, we had 26.66 kips over the same area, 4 inches squared. So that gave me 6.66 KSI in tension. And then remember to box your final answers. And this is well, first of all, any questions on that before I jump into the next thing? Any questions on this? Okay, so the question that was written is why we need the sign when we mention it is in compression. It kind of reinforces each other. In these types of problems, I'm not sure how you were taught this in statics, but basically the negative sign is there to tell you that when you assumed tension, it's not tension. And the positive sign is when you assumed tension, it is tension. So that's kind of where the positive and negative comes from. But when we talk about stress, then it's a different ball of wax. When we talk about stress, negative has a specific meaning. Negative means that it's in compression. It's not like a reaction or a force where it means you made the wrong assumption. When you're talking about a stress, negative stresses mean compression, positive stresses mean tension. And so you put the C and the T on there to reinforce that you and I, the reader, you, the author, and me, the reader, we all agree that this we're talking about is a compressive force. This we're talking about is a tensile force or stress. I'm sorry, compressive stress, tensile stress. Does that help?
Yes, thank you.
Okay. What happens if we are not given the area for the beams? If you're not given the area for the beams, then you can't tell me what the stress is explicitly. You can tell me what the stress is as a number over a variable, but that's all you could do, right? The best you could do is tell me the stress in AB is minus 33.33 over A, and that it would just be a function of A. But you couldn't get to KSI if you don't know what the area is. Okay, I wanted to mention something because I graded the first homework, and I saw one thing that I don't think I docked anybody for this, but I just very politely asked in the comments, please, please, please. And so I'll reinforce that just in case you haven't gone back and reviewed your homework and read all the comments, or on the off chance that you went back and reviewed your homework and you couldn't see the comments. Either way, I want to make sure this is clear. If I toggle back through this problem, and let's go all the way back to the start here. Okay, so what is required? To answer this problem, what is required is the stress in AB and CE, okay? We all understand that the final answer is the stress in AB, the stress in CE. So finding your reactions is absolutely a necessary step to getting to this end goal. But you'll notice that when I solve for my reactions at E and at A vertical and A horizontal, I did not box these answers. Those are not final answers. Those are just intermediate steps. When I came down through here and I found each one of my member forces, I did not box any of these member forces. That's not the final stress we're looking for. These are just intermediate steps. So I got all the way through all these members, and I got down to my final answers, and I boxed the final answer. Please follow that example. Don't box everything, because then boxing doesn't help any more than not boxing. I still got to hunt around for what is your final answer. And it can become very confusing, especially, well, how do I say this politically correctly? Some of you have neater and more organized writing than others. And so it sometimes becomes difficult even discerning what your final answer is, what you meant it to be. And sometimes folks will start going down the path and say, oh, that's not right. And then start over here and go down this path and then end up somewhere over here. I have no idea where your answers are. So please work with me on this. Only box out what you want me to grade, what your final answers are, okay? And does anybody have any questions about that? Okay, so hearing no questions, let's move on. First of all, I did mention this several times, but please go back to Blackboard and look at your homework. Just about everybody, unless you did not miss any answers at all, please go back to Blackboard, look at your homework. I commented on every point I took off. So you should have comments there that you can read and see why is it that you lost so many points on this or that or what have you. Okay, are we ready for the next big topic? Anybody? Somebody give me an okie dokie.
Yeah.
All right. Okay, good. Excellent. Our next big topic is a thing in engineering that's called strain. And strain has a very specific definition. Strain is defined as a deformation per unit length of something. But strain is a measure of deformation. And what we're going to find is that we're going to have really two kinds of strain. We're going to have a normal strain and we're going to have a shear strain. And that obviously is no accident because we only have two kinds of stress, right? We have normal stress and we have a shear stress. Well, for every stress, there's a strain. For every applied load, there's some deformation from that load. No exceptions. There's no way you can put a load on anything and not have some type of deformation. So strain is again defined as a deformation per unit length. So a normal strain, we can have a rod or a bar of some type of material. And we start with an unstressed rod. And what they actually have done in the past is they would put these little indentations or marks established at a known distance apart, L naught. So I pronounce this here is pronounced as L naught, and it's also known as a gauge. So this would be a known distance, 2 inches or 6 inches or whatever. And so this is what you start with. Then if you pull the ends of the rod, then that rod will elongate, or this will elongate the rod, and it will pull the 2 known points away from each other, like so. So if I put a load on one end and I just hold it down for an equal and opposite reaction at the other end, then these 2 indentations will spread apart and you'll have a new length between the 2. So it started at L naught and now it's at a distance L apart. So under the stress, the 2 marks will now be at a length L apart. The average normal strain over the distance between the marks is designated by the symbol epsilon. You're going to see epsilon a lot in this class. It's one of the fundamental things. So this little Greek little e type of deal, Bob, that's an epsilon. And epsilon is defined as the new length L minus the original length L naught divided by L naught. That is the definition of strain. The units of strain, or normal strain, are either inch per inch or millimeter per millimeter. Positive strain is stretching or indicative of tension. So like we just said, positive stress is tensile. Positive strain also is tensile. Negative strain is the opposite. So negative strain would be that the rod is shortening and it is indicative of compression. You can also kind of think of this as a normal average normal strain is how many inches did these 2 ticks stretch apart per inch that they were originally there. So you're looking at stretching in inches per inches of the original material. That's why you have inch per inch or millimeter per millimeter. And yes, I know that inch per inch cancel each other out and you could have no units. You could just say no units, but we don't want to do that. We insist on reporting strain as so many inches stretched or compressed per inch. It keeps us in line with what is it that we're talking about. We're talking about something that is stretching out so many inches per inch. And by the way, these are usually a very small number. Okay, so how do we do this in real life? How do we measure strain? Well, we take a test specimen, we put it in here between the jaws here, and we grip it, and we have a load cell down here, and we have this extensomometer. I knew I wasn't going to be able to say that. Extensometer, how about that? An extensometer is just something that is very, very sensitive, and it can measure the stretching action between the 2 points. So you have a load cell down here, you plug into the computer the cross-sectional area of the sample. So between what you tell it for area and the load cell, it knows stress. And then it gets to strain by measuring the stretching action between a known distance here. We also have another diagrammic way of showing this, where you have the test specimen here, which could look like something like this, right? And so your gauge length may be 2 inches, and you have a known diameter in this region here that gives you a known area. And you have this crosshead thing that pulls the whole specimen down while the top is being held firm. And you measure with the extensometer. I know I'm not pronouncing that right, but for now, until somebody tells me a better way to say it, it's a stretchometer that tells you how much this material has stretched while it's actively being pulled. Okay, does that make sense?
So does it have to have an equal amount of force on each side, or can one side be 50, say, newtons and the other side be 40? Does it have to be equivalent?
It does. It does have to be equal, because if it's not equal, then for every action, you have an equal and opposite reaction. You'd really upset Newton, like Sir Isaac Newton, if it wasn't the same. Another way to say it is that if they were unequal, you're saying if this is 40 kips and this is 100 kips. Well, if that were the case, then you would not have equilibrium. All the forces in the y direction would not equal 0. And so then what you would have is motion. Something would be moving because you don't have static equilibrium. Did I answer your question?
Yes, it did. Thank you.
Okay. Okay. And that's also why you only need one load cell. You only need to know what the load is somewhere along this chain between the action and reaction beams. There's like an action beam, this is a reaction beam. And you only need one load cell somewhere in the chain, because we know that everywhere else in between here and here has to have the same action on it, or else you don't have static equilibrium. Okay, so let's look at a quick little example. If the test coupon, like in the image that I just showed you, has a gauge of 2 inches and it's loaded in the testing machine, and we measure that the elongated length is measured at 2.085 inches, what then would be the average normal strain? Okay, so we fill out our variables. The original length was 2 inches, so L naught is equal to 2. And I just put all the zeros here to keep the accuracy consistent. Your new length is 2.085 inches as given. So your strain is L minus L naught over L naught. I plug in my values and I get 0.04250 inches per inch. That is our average normal strain. By the way, see how this looks like a really small number? But a strain of 0.04250 is actually a really big strain. You'll see that down the line here a little bit, or actually you'll see that in the next lecture when I actually apply this to real materials. But that's actually a big strain. That's a big pull on something. So that is why, generally speaking, when we're reporting strain values, you want to take this out at least 5 or 6 significant digits.
So that number is the equal pull on both sides? Like there's no cut in half, that's just both on both sides being pulled?
Yes.
Okay. Okay,
Yeah.
just making sure.
Okay, well, let me more fully answer that question. That's looking at this guy right here, okay? And there's your 2-inch gauge length. Don't worry about this reduced section. There's your 2-inch gauge length. So what they did is they put this piece of metal into the machine and it actually has these claw grippers that grabs that steel and doesn't let it go. And then the bottom of the machine starts moving. It literally just pulls straight down. And it's not so much that it pulls down with a certain force, it's that it's being moved in a certain distance. It's actually just being pushed down by these giant corkscrews, like so many millimeters per minute. It's moving down. And whatever load it takes to do that is whatever load it takes to do that. So it's not being based on a force, it's just moving. So as this moves down, this sample here is going to resist that movement by resisting a force. So it's going to take a force to move it down, and whatever force that is being resisted by the top bar here. And that force does change. It's constantly changing. That force will start off really small, and it gets bigger and bigger and bigger. So in the example problem that I just did, it started in a totally unstressed condition at 2 inches long. But at some point down the line, this 2 inches became 2.085 inches because we moved this whole assembly down by 0.85 inches. Does that make sense? Yes.
Essentially, is a good way to think of it, is it like for every, like, what was the example that we just did? For every 0.0425 inches of material, it's going to stretch that much. Like, so I'm
You're
not understanding
really
the
close.
concept of it.
Yeah, no, you're really close. You're really close. It's what you're saying is for every inch of original material, it's going to stretch 0.425 inches.
When it's in tension.
Yes.
Okay.
When it's in at this point in tension. So no, you're I was just gonna hit on that. Oh, just lost my voice. I was just gonna hit on that. The original gauge was 2 inches. So this makes it really simple to look at. For every inch of material that's being stretched, it's going to elongate 0.425. That's why you stretched it 0.425 inches per every inch of material. So if the original gauge had been 6 inches, then the total new stretch length would have been 0.085 times 3 or 0.025 times 6. It would have been 6 times as much, but the stretch per inch would be the same. This is a measure of stretching in inches per inch of material.
Another question. If the sample you're testing is in compression, would it be
Yes.
the same value for the same material?
Depends.
It depends on the material.
Totally depends on the material. But if you had compressed it by 0.85, then it doesn't matter about the material because we already have the deformation. So my strain here has nothing in there about material strength or how much load did it take or anything like that. My strain is based purely upon the new length, the original length. Okay, but I think to fully answer your question, if I had compressed it by 0.085 instead of elongated it by 0.085, right, then I can tell you what those numbers would be. L would be 2 minus 0.085, which would be, this would have been 1.915. And so 1.915 minus 2 divided by 2 is minus 0.0425. So the number would have been the same magnitude, but you would have had a negative on there. And that negative is absolutely essential to tell you that that is in compression, not in tension.
Thank you.
Okay. Any other questions at this point? Okay. So let's do example 1. Example 1 is this setup here. I have this beam that is pivoting on a pin at B, and this beam is being supported by a cable that is going to point D. And it's a little, I made this a little small, but this is 40 inches from B to C, and this is 30 inches from C to D. So that's the geometry. The rigid beam ABC is pinned at B, is attached at C with an elastic rod CD, and is attached to a fixed support at D. If beam ABC is rotated 3 degrees clockwise, what is the average normal strain induced into rod CD? That's what's required. Solution. Okay, so we start off with our original length. In the unstressed condition, this rod is 30 inches. So L naught is 30 inches. Now, to get the new length, we have to draw a deflected shape. So I'm going to draw this with the beam going clockwise by 3 degrees. And of course, I have the luxury of using CAD. So all of this is actually drawn absolutely to scale. So this is a rotated beam, 3 degrees. And you can see here at the end that this rod has stretched out by some degree dy. And I know that's a bit small, but that says dy. So skipping for a moment the using of the law of cosines to get the exact solution, we're just going to use the small angle solution with using our sines. So, and we talked about this a lecture or two ago, dy is equal to sine of 3 degrees times x is 40 inches. So dy is 2.0934 inches. And I am carrying a bit more accuracy on these numbers. You'll see why, because when we talk about strains, a very small error can account to a lot. So then L, my new stretched length for L, is the 2.0934 inches plus my original 30 inches for 32.0934 inches. So now I have L and I have L naught. My average normal strain is L minus L naught over L naught. So I plug in my values, 32.0934 minus 30 over 30, and I get a strain of 0.06978 inches per inch. And I didn't box the answer, so shame on me. But that's your final answer for the strain in CD. So again, the concept is the whole rod stretched out over 2 inches. But what we're looking for is how much did it stretch per inch? And the answer is 0.06978 inches for every inch of rod that we have here. Okay? And again, I carried this to 1, 2, 3, 4. That's 5 significant digits, which I would consider to be the minimum for these type of problems.
I have a question.
Yes, please.
So is small angle sine always going to work for these type of problems, or is there going to be times that we're going to have to use the law of cosines?
Great question. Great question. I would say it pretty much will always work as long as this angle is small. And what is small? I'm thinking 5 degrees or less. I think I did a problem one time. I don't recall what I did with it, but I think I looked at 10 degrees. And this answer was becoming noticeably different than the right answer at 10 degrees. So I'm thinking somewhere around 5 degrees or smaller. And I think, to add on to that, I think you'll find that most of the homework problems that look similar to something like this, they are in the neighborhood of 2 or 3 degrees. Okay, any other questions at this point? Okay, let's do another example. Here we have a rigid beam BC that is pinned at B and attached at C. The rod is elastic AC and is attached to A. So in the unstressed condition, this angle is exactly 45 degrees. And you'll also notice this looks very similar to a homework problem that some of you have been working through. And it is similar in that this is equilateral triangle. This is L and this is L. So the problem statement is, if I apply a P down here, such that this angle grows from 45 to 47 degrees, then what is the strain that I've induced into this rod AC? Okay, so to solve this problem, this is one of those things where you want to kind of draw the original shape and you want to draw the deformed shape and put some numbers on this and kind of get your hands around it. But remember the end game. What is it we're looking for? We're looking for strain. And what is the definition of strain? Strain is the new length minus the original length over the original length. So I need the new length, I need the original length. Well, in this case here, L was already taken up by the problem statement, so I used an H for hypotenuse, and I used an H prime for the new hypotenuse. So now my challenge is to come up with what is H and what is H prime. They don't give you L, by the way. L is a variable. So I have to solve H in terms of L. I have to solve for H prime in terms of L. I know what this angle is here because 90 minus 47, 43, but I don't know theta B and I don't know theta C yet. Okay, so does everybody understand the problem statement? Everybody
Yes.
grasped the challenge?
Yes.
Okay, all right. So let's start with the easy one. The easy one is, what is the original length of the hypotenuse, the length of the cable? And we just use Pythagorean theorem, where h squared is equal to L squared plus L squared, because these are equal. And so h is radical 2 L squared, or radical 2 times L. And that's as far as I can go, because I don't know what L is, but I can get it in terms of L. Okay, so now I have H. Now I need H prime. So if I use the law of sines, then what do I know? I know that L, actually, let me back up a second. I forgot to mention something. Because this was a rigid beam's not going to change length. And it was pinned at B, and it's floating down at C. Well, what that means is that what was originally L long is still going to be L long. And what was originally L between the pin and the support is still L. So no matter how much this thing rotates, no matter what this degree is here, this will always be L, this will always be L. Okay, I just want to mention that right from the beginning, because that's the key to solving this, is recognizing that L is still L. So having said all that, L over sine of 43 is going to be equal to L over sine of theta C. See, now we have something that we can start getting our teeth into. So that means theta C is equal to 43 degrees. So now we have that right off the bat. which means if this is 43 and this is 43, then I can find theta B. Theta B is just the 180 degrees is the sum of all three angles of a triangle minus 2 times 43 degrees. So theta B is 94 degrees. Everybody on board so far?
Yep.
Okay. So now I can use the law of sines again. H prime over theta B is equal to L over sine of 43. So H prime over sine of 94 is equal to L over sine of 43. I rearrange so that H prime is sine of 94 L over sine of 43. These are real numbers, so I can calc those out and whittle it down to a 1.4627 L is H prime. Well, there we have it. I have H in terms of L. I have H prime in terms of L. So now I can use my strain equation. Strain is going to be H prime minus H over H, which is 1.4627 L minus radical 2L over radical 2L. All the L's drop out, and that leaves me with a real number, 0.3429 inches per inch. And that is our final answer. Okay, any questions on that example?
Could you please explain again how they're both L's are the same, they don't change?
Okay. Go back up here. Okay, so look at the way that is originally drawn. This is fixed and this is fixed. So this L cannot change. It's between two fixed points. This ABC is a rigid beam. So by how these problems are defined, a rigid beam means that it doesn't deform. It's not going to shorten. It's not going to bend. So a rigid beam BC, this is a fixed length. So no matter how much this thing rotates about B, the distance from B to C will always be L. Did that help? Okay. One last note on this before we move on to the next topic. Notice that P is over here. And we didn't solve for P, did we? In fact, P was kind of irrelevant to the whole problem. But why did we not solve P? And the answer is, we haven't talked yet about some relationship between stress and strain. We don't have that yet. That's actually going to be Thursday's lecture. But until we have some idea of the relationship between stress and strain, until then, we have no idea what P might be. And we have no information about what this cable or rod AC is. We have no idea. This could be a 1-inch diameter, high tensile steel strand, or this could be a wet piece of spaghetti. We have no idea. And that certainly would change how much P it takes to move this thing by 2 degrees. Okay, so that's coming, the relationship between stress and strain and how much force does it actually take to make these movements. But until we get to there, all we have to work with right now is just some indication of how far did it move. And if we know that, then we can get to strain without knowing what the material is or any kind of stress. Okay, so we went all the way down here, and now we get to shear strain. If we start with a solid block of some material, okay, so this is indicating that this is a fixed surface, and this block of something cannot deform along this edge of the fixed surface. So think of this as like a block of rubber that's been glued to the floor. And so you can push on this block of rubber and it's going to deform, but not at the floor where it's been glued to the floor. If we apply a shearing load, so again, this is the load that's being applied up here. I'm pushing this block of rubber over. This is my reaction. So one of these is an action, the other is just merely a reaction. And generally speaking, on the fixed side is where your reaction is going to be. So if I apply this shearing load, then the block will deform as shown, right? So everybody can kind of picture if I was to shove over a lump of rubber, it would just kind of deform into this shape. If I can measure that angle of deformation as theta, so theta is measured from the horizontal to the sloped, deformed shape on the right-hand side of the block, that's my definition of theta. Then the shear strain is defined as gamma, and gamma is defined as from the original shape to the deformed shape. Now, keep in mind that the original shape isn't always going to be vertical or 90 degrees to the horizontal. Keep that in mind. But it is how far did it move under load, that's the measure of deformation. So if it was vertical in the beginning and it took on this deformed dotted line shape, then how far it moved is gamma, and that is a shear strain. Gamma is the shear strain, and gamma is always measured in radians. We don't measure it in degrees, it's always measured in radians. Gamma is defined as pi over 2 minus theta, and pi over 2 is 90 degrees. So you can see the relationship right here. But it's measured not 90 degrees, but pi over 2, because gamma is always measured in radians. Okay, so we have a sign convention here. If the block is shoved over to the right, such that theta, as measured on the right-hand side, is smaller than 90 degrees, then that is a positive gamma. That's a positive shear strain. If it is the opposite, if theta is greater than 90, right, theta is measured on the right-hand side, and if theta is greater than 90, that means it's being shoved to the left, and that is indicative of a negative shear strain. And just a quick reminder that radians is equal to degrees times pi over 180 degrees. Degrees is equal to radians times 180 over pi, if you need to do conversions. And you don't have a fancy TI that'll do it automatically for you.
Yes. Professor, I have a question.
Sure.
So whenever you say that if theta is smaller or larger than 90, isn't that just from like your perspective? Because if you're pushing it to the right and you go on the right side of theta, or on the right side of the form and find theta there, of course it's going to be smaller than 90. But if you're pushing it to the left, can you still measure it on the left side of the, like the edge of the shape? Do you know what I mean?
I do. I absolutely do. And this is a topic that I've really struggled with. And I'm glad you brought it up, because I will be transparent and upfront. I hate this part. I hate the sign convention of shear strain. Don't get me wrong, I don't hate mechanics of materials. I'm not going there. I love mechanics of materials. Though actually, I do use this stuff every day. So it really is, yeah, I like this stuff. But this one topic, this one thing, shear strain being positive or negative, is just annoying. Because I look at this and I say, okay, well, I'm looking at this block, and let's say the block is going north-south, right? So this is north and this is south. Well, then that means I'm looking at the block towards the west. Well, what happens if I just walk around the block, literally, and I look at it to the east? Then this is what I see. Well, did a positive just become a negative shear strain? How does that work? I don't have a good answer for you. This is the textbook definition. So as I'm looking at the problem, if it tends to shove it to the right, and it tends to make a reference angle that is measured on the right-hand side of the block get smaller, that's a positive shear strain. And this is the opposite. But here's the good news. Here's the good news. It's academic. It really is academic. A shear strain doesn't have any difference of meaning, positive or negative. If you are using these principles in something much more complicated, like figuring out the stress field in a sheet of steel, or you're figuring out what's going on in a complicated reinforced beam, then what really matters is that you're consistent, or else all of your equations are going to get thrown off way down the line if you get to something that complicated. But there's no real physical, tangible difference between shear strain positive and shear strain negative. Again, totally transparent with you here. There is, for normal stress, there is a very real, tangible difference between stress and compression and stress and tension. There's a very real difference between a beam that has positive stress on the top or negative stress on the top. Those are very real and different things, but not with shear strain. Shear strain, there's no difference between positive or negative shear strain. It's just a sign convention so that we all report our answers in the same way. Did that help, or did that make that totally depressing?
A little depressing, but yeah, it helped.
Okay, good answer. So this is going to be our sign convention, and I'm going to work through some examples illustrating our sign convention. But just realize that shear strain is fundamentally different than normal strain, and positive or negative do not have nearly the same physical realization as they do with normal strains. Okay, so let's look at an example. Here is an example of a material, and disregard what I said a moment ago about being glued to the floor. In this case, it is allowed to deform out at C here, like you see. So again, we have this problem gives us no indication of where the force was applied or how much force was applied. All it tells us is the green square is our original shape and the dotted square is the new shape. That's the information that we have. And what we want is find the shear strain at each corner. And you can see these angles are different at each corner, so you're going to get a different, possibly a different shear strain at each corner. So let's start with A, the corner at A. And let's find the shear strain at A. So what I have at A is directly measured theta. This is the definition of theta. It's on the right-hand side of the joint here, and it's measured to be 91.5 degrees. So my equation for shear strain is pi over 2 minus theta. So I have pi over 2 minus 91.5, and then I convert it to radians, and I get minus 0.02618 radians. Again, these are generally going to be very small numbers, so you have to report them out to 5 or 6 significant digits. And it is negative because this corner, actually the whole block, is being shoved to the left. So that makes sense that this would end up being a negative value. Gamma D, well, we have gamma D because we already have gamma A. the top surface and the bottom surface are still parallel, so this is still the same angle. So gamma D is going to go through the same angle as gamma A, and so it's the same value, minus 0.2618 radians. For corner C is a little bit different. This is a totally different angle than this angle. So what I'm going to do for corner C is I'm going to define a few variables here. I'm going to define that this is my theta C that I'm looking for, but this is a beta C that I just made up so that I can get my hands around what theta C might be. Beta C is the angle from the slope to the horizontal. Beta C, it can be defined by rise over run. The rise here is going to be, well, see, the total rise is 53 millimeters because I have 50 plus the 3 that it's stretched. So from C to B prime is 53 millimeters. The run is going to be the horizontal translation at B of 3 millimeters plus the horizontal translation of C of 8 millimeters. So the total, if you draw a triangle right in here, the total horizontal is 11 millimeters and the total vertical is 53 millimeters. So knowing this, I can find beta C is equal to the inverse tangent of 53 over 11 millimeters, which is equal to 78.275 degrees. So that's beta C. Theta C then can be 180 degrees minus 78.275 is a 101.725 degrees. So gamma C is pi over 2 minus 101.725, convert it to radians, and I get minus 0.20464 radians. So the math comes out negative, and the whole block's being shoved to the left, so it should be negative. So we're going to just decide together, we're going to call this a negative shear strain. And then lastly, gamma B is equal to gamma C because these two are parallel. So gamma A minus 0.2618, gamma B minus 20464, gamma C minus 20464, gamma D minus 0.2618, and I boxed the whole answer. Okay, any questions on example 3? Okay, and average normal strains. Okay, so we're out of time, which is okay. We're going to stop at slide 171. And we'll pick that up next time. Before I end the Zoom meeting, does anybody have any final questions they'd like to ask? Okay, not hearing any. I will thank you all for tonight, and we'll see you on Thursday.
Thank you, Professor.
Thank you.
Thank you.
Thank you. See you on Thursday.